we have another problem here. It says what the value is of the hydronium ion. So we'll go ahead and we'll write that down. H3O plus concentration is 5.9 times 10 to the negative third. Yes, it's molarity. They have also said what the molarity of the solution is. So we're thinking that HA, at least initially, originally, was 0.050 molar. They ask what's the pH of the solution, the percent ionization, and the Ka value. All right, well, let's think about what's happening in here. This is a case, again, where the HA is being combined with water, going into an equilibrium, forming the A minus, the anion, and the hydronium ion. So, if that's true, every time one of these falls apart, I'm making one of these and one of these, then I should also be using this same number for the anion concentration. That means the easiest thing for me to do next is find out the Ka. If I'm doing the Ka, I need to have the actual concentration of HA at equilibrium, not this original one. Oh, that's easy though, because I know exactly how much fell apart, right? So I should be saying that HA now is the original amount, and I will subtract this guy, which, well, since he's in scientific notation, that's not really a very good way to write it. So I'm going to be writing 0.0059, because that's what it means, right? This only goes out to 3 sig figs. So I'll be saying 0.050 minus 0.006 is approximately correct. So I'm saying that this then should be 0.044 is what I should use in my formula. Let's put that in then. Here we go. There's the Ka. It should be these two on top, right? Hydronium ion and the anion over the concentration of the acid. I have all those numbers now. So 5.9 times 10 to the negative third is going to get squared. And I just figured this out. So it's 0.044 down here. Hit my calculator and I get this, because I don't trust it past 2 sig figs. Wonderful. What else can I do from this? Well, what else are they asking for? Oh, the pH. Well, I could have done the pH first, because they had told me this, right? It's minus the log of the hydronium ion, which we already know is minus the log of 5.9 times 10 to the negative third. I hit my calculator on that one, and I'm going to get a pH of 2.23. These are the two that make the significant figures. This is really more indicative of what the exponent was, remember. So I've got those, and then it says, what's the percent ionization? Well, the percent ionization is going to be that hydronium ion concentration, right, over the original HA and multiplied by 100%. So if I put those numbers in, I've got the 5.9 times 10 to the negative third over the original, which was 0.050, and turning it into a percentage. Put that through your calculator and realize that you have only 2 sig figs. You're going to come up with 12%. 12% actually dissociates. A pH, and then I want to know what percentage of molecules have ionized and what's the Kb value. Okay, I have to think just a little bit about that. They've told me that the pH is 11.86. That means that if I want to know the pOH, I'll take 14.00 and subtract the 11.86, and I will get 2.14. This will then allow me to figure out what the concentration of OH minus is. So that will be 10 raised to the negative pOH, right? So 10 to the negative 2.14. Put that through your calculator and you're going to get 0.0072. 2 sig figs, because that doesn't count as a sig fig. That's just telling you how far you're moving things. 2 sig figs from here. So we have that figured out. That should help us figure out the percent ionization then. Okay, so the percent ionization, since this is a basic thing and we're looking at OHs, it was hydronium over the original. Now it's going to be hydroxide over the original. So we're going to do it that way. Well, how much hydroxide over the original? And turn it into a percentage. So we'll put those numbers in. 0.0072 divided by the original, which was a 0.100, and turn it into a percentage. You're going to get 7.2% when you get all done with that. We still need a KB. To do this, I need what the value is now, right? These are going to be the same number. All right. What's that number? Oh, it's right here. Okay. So these top ones are both 0.0072, and that's going to be squared. What's this bottom one, though? It's not the original. Oh, here. There's, okay, 0.100 is the original, but some of it was used up. So we're subtracting 0.007. I'd like to put the 2 there, but it wouldn't. My sig figs would mess up. So I'm going to say 0.093. To the extent my sig figs will let me do this. And fill that in there. If I then hit my calculator, I'm going to get a KB value of 5.6 times 10 to the negative 4th. Now, I didn't really mention this, but I might want to, because this one wasn't, this was a base, not an acid. So it's a little more interesting to try to see what it is. You know, it was easy enough when it was HA and water becoming the anion and the ammonium ion. What is happening here? Well, I just want to write this down. This is what I put in the water. There, and there's, whoops, there's the water. This is being a base, forcing this to be the acid. So it has to give up an H+. That means this is going to become C2H5NH3 and a plus. And then this is going to be like that. Just to clarify exactly what was going on in the actual equilibrium.